Problem number 51, and queens, one of my favorite problems. So this problem gives us basically wants us to find a way to place n queens on an n times n chessboard such that no two queens attack each other. So we are given an integer n, so this n will represent how big the board is in terms of the row and columns. And we have to return all distinct solutions. And we may return the answer in any order. These are just general rules. So yeah, so each solution will contain a distinct board configuration. Blah 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 blah. Basically, it looks something like this, right? We look at example 1 at this position, at this one. So we have at index 0, 1, 2, 3. So this is the first index. The last one is over here. First one is over here. Third one is over here. And then for the second one, we have the same thing over here. Okay. So nothing else interesting, but overall, my approach to this solution is to use a backtracking and recursion. I think this is the only currently my favorite way to do it, at least. So I have a board. So notice how my board is actually a vector of int. So the way I'm going to store the queen's position is by using, so let's say I have a 4 times 4 board, then I will have 4 numbers here. So each position over here would represent the y value, right? So for this instance, for this board configuration, the first one will be at index 1. So we do something like this, 1, and then this one will be at index 3, 0, this one will be at 0, and this will be 2, right? So this is basically a board configuration stored in a single list of integers, right? So that's how I plan to do mine. And then later on, when we found a solution, then only I'll convert it into the format it wants. Okay, and then we have a PD vector of string called result. So this is what we are going to be returning as a answer. Okay, so let's see what's up first. So first thing first, I initialize my board. I resize it to however long the board is. For let's say this board is 4 times 4 long, so I'll resize my board with like this, right? It will look like this. Basically 4 integers of value 0 right over here. Then I start the recursion. So this recursion part is the complicated part is over here. This is just when we have found a solution, right? So for now, we don't need to pay attention to this first. So let's look at this for loop here, right? So this for loop here, I'll be iterating through. I'll be testing every index up to n, right? So right now my board looks like this. Let me get my mouse. So my board looks like this, 0, 0, 0, 0. And then you know what, I'll draw out the board as well. Okay, so my board looks like this. Everything is empty, initialized at 0. So here I'm testing the index. Here I have a boolean, right? So the way I check whether or not I can place a queen is through this small block here, right? Okay, so for every row, when I want to place a new queen, I have to check every row to see whether there are basically attacking queens. So how I do that is, over here is where I have the iteration, so starting from 0 all the way to the current position I'm at. And since position is starting at 0, right, so position is at 0, and this can place is equal to true. Okay, this is just my way of writing. Obviously you can do this same thing, right, technically the same thing. So the way I check is this one, this line here, board previous position equals to testing index. This is to check whether or not there are queens in the same row, right? So that's to check whether or not there are queens in the same column. I mean, so this is a column. So by that, it's basically checking whether or not we have like the same values here, right? Basically the same thing. But since the board of previous port is now 0, so the board is just now it was 0, right? And then our testing index is also 0. The board previous port is 0, and then up to position. So here position is 0. So technically at the first time we don't need to check for this. So can place is true. We place down our queen. Board position is equal to testing index. So our first queen has been placed down, and then we recurse, right? Position plus 1. When position reaches 1, we ignore this first. Then again we check testing index. We enter another recursion, enter another for loop. We check again for can place, and now when we check previous pos is less than position, right? Previous pos is 0, position is 1. Slide up a bit. Position is 1. So we first test this. So previous position is actually 0 already, right? So we cannot place a queen over here, right? We cannot place a queen here because there is a queen on top of it already, right? So can place equals to false. We break out of it. This will not trigger, and we just plus plus, right? Plus plus the index. So now we're testing at this position instead. Okay. Then we test again. So board previous position is not equals to the testing index, right? So now the testing index is equals to 1. But, so let's say if I were to place a queen here, right? But if I were to check over here, so this part of the code is to check whether or not our queen is being attacked adjacently, right? So if we do some manual checking, so the board of previous pos, right now previous pos is 0. So 0, so the absolute value of 0 minus the testing index of 1. So this will give us 1 is equals to the absolute value of the previous position, which is 0 minus our current position, which is 1, right? This will give us 1 as well. So what this means is that there is a adjacent queen. So when there's adjacent queen, we obviously cannot place a queen down. So that's why we have to make can place equals to false and break out of it, right? Once you break out, our testing index will increment once more. And over here, now that all of this passes, we can place down a queen, right? You see here, all of this passes, we can place down a queen. That means so far we are doing great. There's no uh, problems whatsoever for now. But on the next turn, you notice that we cannot place any queens anymore. Right? We cannot place here because it is being obstructed by this queen. We cannot place here because it's being attacked adjacently by this queen. Cannot place here, same reason. Cannot place here, same reason, right? So what we have to do is we backtrack back to position 1 over here. And now, instead of placing it here, we are going to place it over here. Right, so that's when this recursion breaks out, testing index will increment, right, to 3. Okay, so this will become 3. And then basically this will basically repeat. Try to put here, check, cannot put, try to put here, check. Oh, we can put it, but on the next iteration we cannot put it here because of this. We cannot put it here, cannot put it here, cannot put it here, right? So we have to backtrack all the way to our starting queen, and then only try the next move. Okay, so from this starting queen, we cannot place these 3, but we can place over here. Over here we can place 1, and over here we can place 1 more, right? So in the end, this board configuration will give us the board of 1, 3, 0, 2, like I mentioned just now. Okay, and then when position will eventually reaches 3 or 4, right? That means we have finished putting a queen down here, and we're moving to the next, and moving to the next row, right? But there is no next row. So what we do instead is we print out, or more like we push the result of this board configuration into our result vector, right? So the way I do it is I have constructed a vector of strings. So it will look exactly like this. So my string will look like this. And let me just make a new one. Right. Right. So it look like this. You see it tracks similarity to my initial board, but instead we are working with just some numbers. Okay, so for every iteration, I make that into a queen. So for example 1, so I change this into queen. 3, I change it into queen. 0, change this into queen. And 2, change this into queen. Once I'm done with that, I push back this current vector into our result. Then we'll have something like over here, right? So we have one of it solved. So that will return. This will end. Okay, sorry. So this will end. We cannot put here. And then it will backtrack again, trying out the next queen position, which is over here, right? And then what it will do is just repeat itself, repeat the recursion, testing every row as it goes. Eventually we reach another configuration. We convert it into an array of strings, push it into our result. And once we're done with that, we've finished trying out all the possible queen positions. And then we exit the recursion and return the result, which in this case, it will give us over here, something like this, right? Okay, so all in all, at first this kind of problem was needed a bit of thinking, especially the checking part, right? I would say checking the diagonal part took me the longest, right? The best way to check whether or not there is a queen diagonally at both sides at once This took the longest. Other than that, the recursion part, the backtracking part, they're all the same, and they're all pretty similar to the previous exercises that we have done before. Alright, that's enough of talking. Hopefully my solution intrigues you and that my explanation was sufficient. Thanks a lot. That's all I have to show. Thanks.